I'm going to hand it over to Matt Topol from Voltron Data. Again, he is the author of In-Memory Analytics with Apache Arrow with the talk, Understanding Apache Arrow. Matt, the stage is yours.
Hey everybody, and then let's hello. Can people see and hear me? There we go. I think I'll share my screen. And cool. So hey, look. Back. So hey everybody, I am Matt Topol. Yeah, I'm going to give a talk, just understanding Apache Arrow, basics, just understanding how it all works and what it is. So who am I and why should you listen? Well, I wrote the book on Apache Arrow, apparently. Yay. They're giving it out a free copy. So, it'll be fun and great. I used to work at FactSet Research Systems, which is a financial software and data company doing data analytical development, distributed systems, and service. And now I work at Voltron Data to work on the Arrow libraries directly. So, what is Apache Arrow? So let's do a quick primer here. Arrow is a high-performance in-memory columnar format, and there's implementations exist in a whole mess of languages, whether you're working in C++, Java, Python, Go, Rust, R, and a bunch more. You can use Arrow because the libraries exist. The benefits here is that it eliminates the need for the serialization and deserialization of the data. The reason why Apache Arrow was created in the first place was the co-creators, Wes McKinney and Dremio, noticed that the time spent in a lot of systems was heavily used by serialization. And as a result, if you could eliminate that serialization and deserialization as you pass data from system to system, you can get a hell of a lot of performance speedups. So you can see two images here. On the left side, you have an example of what happens when everyone's using their own proprietary or specific or their own formats. You have to copy and convert, and you're paying costs as data goes from system to system. With Arrow, the representation in memory is identical to its representation in the over the wire, and identical in whatever language you're working with. So therefore, the memory can just be passed as is from system to system, whether you're working remotely or you're working from different processes in the same system. Arrow is increasingly being more highly adopted. It was started back in 2016 and has just exploded since, and is increasingly being used in the data science and analysis ecosystems. Here's an example showing you just downloads of PyArrow, and you can easily see its exponential growth of people just downloading the Python implementation. So let's talk about why Arrow gets that benefit. What is it? What is the benefits here? So to do that, we need to talk about column-oriented memory first. What is columnar? Columnar is a way of representing a table of data. You can see here we have an example of a table, and on the left side you have your traditional row-oriented buffer of memory. You have your individual structs. Maybe you have a struct that has an archer string, a location string, and a year integer. And then to represent the table, you just have an array of those structs. And then in memory, it looks like that buffer right there, where you have column 1, column 2, column 3, column 1, column 2, column 3, over and over for all the rows. In a columnar representation, column-oriented situation, you have the columns grouped together rather than the rows. And that's how Arrow represents memory internally. Now, why is that beneficial? What's the benefit there? And the idea here is memory locality and vectorization of processing. Along with the libraries of implementing the format, Arrow provides in libraries for computation and analytics, and it be named Acero Arrow computation engine. With memory locality, the idea is you have to traverse less memory to perform operations. So, for example, if you wanted to get all the archers in Europe from that previous table, you only need 2 chunks of memory. You don't need to read every single row. You don't need to read the entire table just to answer all archers in Europe. You only need to spin through that one chunk of locations, get indexes, and then get the archer strings at those indexes. That means if your table's not in memory, you can read less of it off the disk. If your table's in memory, you only have to pay the cost to pull that into the processor registers for those 2 columns, not for the entire table. Not to mention that when you're iterating through that location column, you're not jumping all over around in memory. The processors will always benefit if you can stay closer in memory, because they always pull chunks of memory at a time. In the case of our second example here, say you wanted to just calculate the average year across all those rows. You can benefit, and Arrow is designed to benefit from vectorization of computations. For example, SIMD is an example, single instruction multiple data. And to do that, you need contiguous chunks of memory, which is what we have. So, is Arrow just yet another tool thrown in the toolbox of all the various data science tools? Well, let's see if it deserves the spot there. Arrow has interoperability. It has the Python Arrow implementation, easily converts to and from the common pandas data frames, and often can be done without having to copy data at all. It also slots easily with NumPy. So, in addition to that, the other implementations also try to interop wherever they can amongst the different tools that are already existing in the ecosystem. So let's look at an example. Spark. If you're familiar with data science, you've probably heard of Spark. You probably are familiar, at least basically, with what Spark is as a distributed computation engine system. Now, Spark is written in Java and Scala, and therefore runs in the JVM. So when you're interacting through PySpark, for example, this is a slightly simplified way of looking at how data goes from one to the other. You have your Python application, which is going to read your data. Let's say, for example, a 4 GB CSV file, and go create a pandas data frame. We send that to the Python Java gateway, and then it's got to serialize and copy all that data to the JVM. It can't just hand the bytes as they are. It needs to put it in a format that the JVM can understand and that Spark can use. So you have to pay for that cost for the copy. Then it sends it to Spark. Spark does whatever you wanted it to do, and then the results go back. But that means that it needs to get reserialized back to a format that the Python can use, which means another copy, which means performance. Spark implemented an option to have it use Arrow internally and natively for certain operations where it can. So if we read that 4 GB CSV into a stream of Arrow record batches, and we pass that using Arrow's IPC, interprocess communication format, to the Python Java gateway, it can just hand the raw bytes, the memory as is, to the JVM. No copy, no serialization, nothing. Just gives a pointer to the JVM and say, here's your memory. Java then uses that. Spark then manipulates, does whatever it wants, creates or operates, that's what it generates, and then sends it back. Same idea. The memory it has can be just passed as a pointer over to Python, which can then interpret the bytes as they currently exist. No copy needed. So, but that is an example. When should you use Arrow? When should you not? Like, what's the use cases that actually really benefit from it? To address that, let's oversimplify a little bit. When you're working with data and you're working with systems that are passing data around, there's a few different complementary but competing things that you're trying to optimize based on a type of format. Different data formats, you're trying to deal with the size, the cost to serialize or deserialize it, and how easy it is to use. Yes, these are very overly broad, but stay with me. Now, among the common data formats, I've kind of extremely broadly dropped these into three different ways of categorizing them. You've got your persistent storage, you've got your runtime in memory formats, and you've got your message passing formats. And on the slide here, you can see a couple different examples of where certain formats fit into the categorizations. Some are optimized to better be for persistent storage, which is where you want to typically optimize either for the read or the write costs. You're going to want, smaller size because you want lower I/O when you're reading from the disk. You want to optimize to minimize the amount of data that needs to be read to satisfy a query. You want to deal with I/O bottlenecks. When you're talking about message passing, you're typically optimizing for passing small messages between different processes, either on the same machine or across the network. So you want those messages to be very small so that you're spending less time sending the message or sending across the wire or network. For example, the official documentation of Protobuf says that the optimal message size is less than 1 megabyte. Now, with message passing, that cost of serialization and deserialization is also very important because you want to have a lightweight message passing protocol to go with your lightweight small messages because you want to be quick past that small bit of information. Finally, you have your runtime in memory processing where the idea is that you can operate on that memory as it exists without having to transform it before you can operate on it. Here's how you can view the relationships between all those formats. Your data is either in the cloud or on disk or wherever it happens to be. And you want to get that data and do something with it. You have a bunch of Parquet files or CSV that you want to process. Well, you have to get that data. You have an I/O cost, whether it's across a network or a disk or whatever. Then you have to decompress it, deserialize it out of its storage format so that you can then perform operations on it. Because maybe it's compressed data like Parquet, or maybe it's all text like CSV, and you want to perform operations like computations, so you need to actually convert to something you can use in memory. On the other hand, you have your message passing formats. Let's say Protobuf. You can pass that Protobuf message across a shared memory or network I/O or whatever, and then you have to deserialize it before you can operate on it. There are some message passing formats like flat buffers, which allow you to operate on the memory as is without having to deserialize it, but that's few and far between. But then again, Arrow does leverage flat buffers for its messages. And finally, that in-memory runtime format is that message is the way the memory is represented when you're operating on it at the time that you're on. And that's where Arrow is focusing. That's Arrow's goal. So let's look at a couple examples again. Manipulating memory and controlling memory is highly important. One example that Arrow makes possible because of the fact that its representation is that in-memory column-oriented format is it allows you to memory map it very easily. So let's look at, say you have a 1.8 gigabyte CSV file. This is an example straight out of my book. You have pandas, you want to read it, you have millions of rows, and you want to read one column from that data set. You can use pandas read CSV. You can use PyArrow's read CSV. You can have a Parquet file. This particular data set translates to about 286 megabytes of compressed Parquet. Or you can use Arrow's IPC format. Arrow's IPC format allows you to memory map it, which you can do with PyArrow. So, if we measure that runtime and memory usage to read the column and create a pandas data frame, you get this. Now, I'm not going to go into heavy depth here, but all the code samples and examples of actually doing this yourself to see this yourself is in the book. But what you can see here is when we memory map that IPC format, the actual physical memory used to read that one column is virtually nothing. And it runs in about 200 milliseconds. If you use the Arrow IPC format without memory mapping it, you can see that that memory usage there is basically the entire size of the file. It reads the whole IPC file in, and then you can use it. So it takes a bit longer. On the Parquet example, it only uses about 194 megabytes of memory to read metadata, read the column, deserialize it, decompress it, but it runs pretty quickly because that's what Parquet is designed for. Now, the raw CSV file, you can see here, if you're going through pandas directly, it only uses about 1,200 megabytes. It's a bit cheaper, but it takes 20 seconds, a hell of a long time. Now, PyArrow's CSV reading does multi-thread and multi-thread the read. As a result, the final table of data can't be converted directly to a pandas data frame. It needs to be copied into one contiguous chunk for pandas, because so you're sacrificing memory for performance there. But the goal here is showing the benefits of the idea that Arrow, when you properly manage your memory, can be super fast. So just to sum up before Jason takes over and talks about the data transport methods a bit more, your two major types of use cases for Arrow are when you're transporting lots of data and when you want to perform analytics or analysis on that tabular data. To facilitate that transport, in addition to that IPC format, Arrow defines protocols for streaming the data, such as Arrow Flight and Flight SQL, which is what Jason is going to talk about shortly. And then, as I mentioned, Arrow libraries include Acero for Arrow native compute. You've got different APIs, like the C API, to add interoperability for applications to easily integrate with Arrow. You've got, and then you've got to take advantage of all that column representation, vectorization, and performance. And that's really what this comes down to, is how can you make your performance as good as possible with as little memory as you need in whatever environment and whatever tools you're utilizing, whether you're a consumer of Arrow as a data scientist or whether you're an engineer building utilities. Arrow is going to benefit you in some ways, and I highly recommend looking into it and utilizing it wherever possible. And with that, I'm done.
Okay, Q&A time. We've got a couple of really fun questions for you, Matt. The first question is, and this is a fun one, is Voltron one of the rarely mentioned transformers?
So you might be familiar with Voltron, the show from a very long time ago, which involved a series of robots forming together to form one big robot. And Voltron, the company, Voltron Data, formed as a result of about 3 or 4 companies basically coming together to form one company to continue doing data with Arrow. And that would be Blading SQL, the NVIDIA Rapids team, Ursa Lab Computing, and I wish we got the fourth one. But it's that combination of things that brought together, and that's why they called it Voltron Data.
That's awesome. Is there a way to visualize the memory access patterns of a program to verify that your code is causing contiguous columnar memory scans? Like, how do you practically evaluate this versus going, yeah, I know in theory if I do this, it should work?
It's going to differ based on what programming language and environment you're working in. Every environment has their own utilities and tools for that, and the rules of how certain allocations happen are going to be based on that. But the best way as far as evaluating it is always going to be to just look at, run your program and look at how much memory is it using, how long did it take to run, and if it didn't work, then debug and investigate why. But the method to debug it is going to differ if you're using C++ than if you're using Python, if you're using Go. So there isn't really one answer I can give to that one. It's very much going to depend on your environment.
Got it. How much of Arrow's benefit is due to choosing the appropriate level of data granularity? Is it more efficient with low-level data than with aggregated or semi-aggregated data? How much data would need to be re-architected to see the benefits?
Like with any kind of data analysis situations there, it depends on what you're doing. And it basically comes down to the matter of, caching versus memory versus time. Arrow's benefit is that performing analysis is faster, and transporting the data between systems is faster and cheaper. Now, if you pre-semi-aggregate the data, that just means that when you perform the aggregations to get the final list of data, that will be faster because you already semi-aggregated it to begin with. The cost there is you have to store that semi-aggregated data. So the Arrow's benefit is, regardless of choosing the appropriate level of data granularity, it's in addition to it. You're going to, whether you're aggregating the low-level data or you're storing the semi-aggregated data, Arrow can benefit you in either case.
Okay. Is there a benchmark between using just Spark and Spark with Arrow comparing the processing time?
I don't know if there's a public one, but there's an example with a benchmark in my book, complete with sample code and the chart and a chart showing performance, and it shows exactly that. It's using just Spark and using Spark with Arrow, and also an example using a user-defined function for computation.
Yep. So again, remember, you can pick up that book on Amazon. It's from Pack Publishing, and one of you guys will be winning a free copy today. So stay tuned to the very end when we'll announce the winner. And one last question: is Apache Arrow suitable for PCAP files?
Oh, so Arrow is suitable for representing any complex type. I haven't worked a ton with PCAP files myself, but if you're going to, the problem with using Arrow for a PCAP file is that I doubt that a lot of utilities that currently exist for PCAP files have implemented Arrow yet. So you lose some of that interoperability with the existing utilities. But I could definitely see Arrow as a suitable in-memory representation for them. Again, remember, Arrow's goal is primarily for that in-memory representation rather than a storage format like Parquet. Parquet is primarily a storage format to make it easy and fast for reading data in, whereas Arrow you can consider almost the in-memory representation of how you would represent, say, Parquet data.
Awesome. We're out of time for questions. Again, I want to say thank you, Matt, for coming today. That was a fabulous conversation. There is a couple more questions that are in the chat for you if you want to take a look at those. But yeah, again, I just want to say thank you. And again, everybody, remember, we are here to give away a book. So at the end of this whole thing, we're going to be announcing someone who's be winning this in-memory analytics with Apache Arrow book. So do stay tuned. Next, we're going to be